Well, thank you everybody for joining us this afternoon. My name is Maria Hadlow and I am the editorial director of Lift and Hoist International. Now, I've only just started learning about hydrogen embrittlement, but fortunately we have with us today some very eminent people whose knowledge on the subject is way outweighs mine, and they'll be able to share their expertise with you. Now, it's because of the absolute importance of this issue, particularly for those working in offshore environments, that William Hackett wanted to highlight the cause and effects of hydrogen embrittlement, or HE, as you will also hear it called today. Now, understanding the mechanics of this type of corrosion will help reduce the chances of unforeseen failures, which will in turn make the industry safer and prevent expensive product delays. We hope that this webinar will add to your knowledge of HE, and you'll be able to take that knowledge back to your companies, share it with your customers, with your suppliers, and use it in future projects. Now, I'm now going to ask our panelists to introduce themselves and provide a brief insight into their own work with hydrogen embrittlement. Now, I'd like to start with Professor Rolf Mostert. Now, Professor Mostert is head of the Department of Materials Science at the, of Material Science and Metallurgical Engineering at the University of Pretoria in South Africa. Rolf, would you tell us something about yourself and your work into hydrogen embrittlement, please?
Thank you, Maria. Well, I've spent 35 years in industry, first with our local steelmaker, ArcelorMittal, and then at an engineering consultancy before I joined the university. During my years in the consultancy industry, I've come across a number of hydrogen embrittlement failure analyses, and I then also gave expert testimony regarding hydrogen embrittlement in a number of big legal matters in South Africa. At the university, we have a number of hydrogen embrittlement projects going on. Some of the work we are doing is investigating the influence of laser shock peening on hydrogen embrittlement susceptibility, also studying the impact of tempering treatments and hardness on the hydrogen embrittlement susceptibility for a number of alloys currently. So I think that's more or less a brief summary, Maria.
Thank you very much, Rolf.
Good.
Now we also have with us Francois Stridon. Now, Francois is a metallurgist and the production and technical manager at McKinnon Chain. Now, Francois, can you tell us a bit about yourself and why hydrogen embrittlement is such an important consideration at McKinnon Chain?
Thank you, Maria, and thank you for the opportunity to be part of this interesting discussion. As you said, I'm the technical manager at McKinnon Chain, a division of the Score Metals Group. I've been with the company since 2006. My main focus areas currently is quality management and product and market development. Now, prior to joining the Score Metals Group, as in the case with Professor Mostert, I've also been with the ArcelorMittal steelmaking group for 25 years, where I obviously gained a lot of experience in steel manufacturing and related matters. McKinnon Chain have been actively involved with the development of lifting products for the offshore market over the last few years, and also with William Hackett as a partner to that. And we recognize the challenges and risks associated with the offshore environment. One of these challenges obviously being hydrogen embrittlement. To us, it's therefore very important that we as manufacturers and in general the offshore industry understand the risks of this harsh environment. It's important that our manufacturing processes and the acceptance criteria for these products are aligned to meet these risks and to mitigate this risk. That's important for us. Thank you.
Thank you very much, Francois. And Mark, if you could, sorry, I better introduce Mark. Mark is a specialist lifting engineer at marine operations at Total. And Now, Mark is remote from us today, well, very remote, so we have no visual for Mark. But if Mark, you could tell us a little bit about yourself and your work at Total.
Good afternoon, it's Mark Taylor. I'm in charge of all lifting operations for Total in the Aberdeen area, looking after all the assets that we have on the UK shelf. We got involved with hydrogen embrittlement issues 3-4 years ago, where we identified it was becoming an issue with lifting equipment and failures. And with Hackett and a number of other suppliers, we put limitations in to try and prevent failures of lifting equipment on our sites. Total worldwide is being very keen to ensure that this issue is identified and is recognized by everybody in the industry because of the risks associated with this, because it's something that you can't inspect for, you can't anticipate. So it is a big risk to lifting operations worldwide. Thank you.
Now, we're also hoping that Dr. Emilio Martinez Panedo will be joining us. He's having a few technical problems getting to the meeting. So when he's able to, we will introduce him. But even in the meantime, I think you will agree that we're blessed with a wealth of experience to ask all your questions about HE. So before I introduce our main presenter, just a little bit of housekeeping. If you could type any questions you have into the drop-down question and answer menu at the bottom of the screen, and I will collate them and ask them of the panelists at the end of the presentation. If you could also include your name and email address, then if we don't have time to get to your particular question, I'm sure our panelists will be happy to answer you privately after the session. So now it is my great pleasure to introduce Ben Burgess, who is Director of William Hackett. His presentation, Offshore Lifting Materials Guidance, covers materials and products for topside and subsea lifting applications, where hydrogen embrittlement and hydrogen assisting stress cracking are recognized hazards. Ben, it's over to you now.
Thank you, Maria. Let me just bring up my presentation and hopefully the technology will work. Can everybody see that? I'll take it if the panels can see it, everybody else can see it. Is that good? So good afternoon, everyone. I am Ben Burgess, one of the directors at William Hackett. I hope this afternoon finds you safe and well in these uncertain times. To start with, I'd like to say thank you for choosing to invest your time with us this afternoon. It's a very important subject, and by the number of attendees, it's a global issue that spans all sort of operations and all territories. I want to be clear on our objective in sharing the technical report. It's to make the industry a safer place and to make it operationally more efficient. We're sharing this information publicly with both our distributors who we go to market with, to our end customers, the likes of Total, Shell, BP, Conoco, Technip, Subsea 7. They all have access to this, as indeed do our competitors. And we have chosen to take this approach to make it completely open and share our IPR, because we believe that this is the only way to effect change in the industry and to make it a safer place. And what we've seen is that a number of bits of feedback are happening from other manufacturers now as a result, and we take this as a positive response to the stance that we have taken. In terms of the attendees on the bridge, we've got folks going from Australia through Asia, Middle East, Europe, the UK, all the way over to America. So it's obviously late in the evening in terms of the guys down in Australia. In terms of a quick introduction to William Hackett, before I go into the slides, we have been manufacturing chain-based products in the UK. We still do that to date. But in terms of our high-grade lifting solutions to date, we work with industry partners who we believe are best in class. So McKinnon in terms of the chain-based products and the master links. We work with Yoke out of Taiwan in terms of the forged products. We work with FEC in terms of some of our Hoist low chain, the fine tolerance products, and on stainless steel products with Kett and Walder out of Germany. So we bring together a lifting bundle of goods, a range of solutions for the specific industries. So let me kick into the slides, and I'm going to try and get through these in around 15 to 20 minutes. If any of you at the end of this session raise questions or would like a deeper dive into any of these areas, please feel free to just message Maria, or to contact me directly on the matter. So the agenda that we're going to follow through, if my slides will work, covers here. I'm not going to read through the agenda. I'm going to just go straight into it, which is perhaps a very obvious statement. Most of the international standards, such as EN 818, such as the ASME standards, relate to lifting applications and products in an onshore environment. Okay, and in terms of when you're lifting in an onshore environment, it is significantly different to an offshore environment. And it's that knowledge of that environment and the application which we believe has to be understood to make a safe product that's reliable for that environment. So onshore, typically, everything is known. You're lifting from a static location to a static location. The loadings are all known and understood. Okay, there should be the ability to store and make available the products is very easy. Offshore, it's unknown. You have the corrosive environment, you have the effects of the ocean, the sea, the currents, etc. So loads are not static, they are dynamic. The likelihood of a shock load occurring onshore should never occur. Offshore, it has to be factored into the equation all the time. So we believe that in offshore, you're looking for different attributes from your products. Okay, so we believe that offshore toughness is the most important attribute of the material. So toughness and ductility in the offshore environment are paramount. In terms of tensile attributes and factor of safety, you should cover that with your 4-to-1 and your 5-to-1 on your additional products. So toughness and ductility is where we focus offshore. So just to kind of nail exactly what hydrogen embrittlement is and hydrogen assisted stress cracking. So hydrogen embrittlement is the phenomenon that's caused through a loss of strength and toughness in the steel through the introduction of hydrogen into the material and thus making it brittle. So if you look very carefully at the slides here, we've all seen chain and steel-based products offshore. You cannot control the hydrogen, the corrosion that takes place. So as the corrosion takes place on the surface, the hydrogen molecules, the atoms, then diffuse into the steel. And as they do so, they create internal pressures. We don't believe this can be avoided, and therefore you have to look at the solution differently. We believe there are 3 areas of focus here. The hydrogen source in the bottom left cannot be avoided. We have to plan that corrosion is going to take place. At the right-hand side, the mechanical stresses of the load will always be being applied to the product. It's what it's designed for. That cannot be avoided. The only thing that you can control is the material that's being used and its susceptibility to hydrogen embrittlement and the other pressures that are exerted on it offshore. So this comes back to the steel making process, the raw material, the tempering, and all these other processes. And we will go into that in more detail if you wish on the Q&A in terms of the panel. So we believe that you have to start with material susceptibility. It is the only area that you can control. So what happens as the hydrogen molecules and atoms go into the steel? They're drawn towards the grain boundaries, the dislocations, etc. And they gather at the areas of greatest stress. Typically, that's around the crown of the product. And as they do so, they create internal forces, okay? And those internal forces start to and can then reduce the effective working load limit or load-bearing ability of the product. This comes down in simple terms to the grain structure. And I'm going to give you a very simple analogy. Apologies for the technical members of the audience today, but for the ones who perhaps are not conversant with the subject, it's as follows. I'm sat at a wooden desk. I have a hammer and a nail. If I hammer the nail into the wooden desk, the grain structure of the wood will accommodate the ingress, the forced entry of the nail without the wood breaking. Okay. If I have a glass desk, which is harder and the grain structure is different, and I do the same process, then what will happen is as the hammer hits the nail and the internal forces happen into the glass will shatter. The grain structure in the product is not designed in that way. So in a very simple way, what we have to do is to design a material and products that will deal with the corrosion and the mechanical stresses that they will inevitably be faced with in the environment that we're going to put them into. So I just want to touch very briefly. This is a global issue. The companies that you see referenced here have all issued public safety alerts on the subject. And we've worked with a number of these and many others on this. In terms of our approach, we try to take a consultative approach, advisory approach, and we distinguish that from product sales as to what we're doing here in terms of sharing our IPR. And at times, some of these organizations take some of that IPR and they then put it into product specification, which is always advised to be non-brand specific and issued to the marketplace, because we believe that is the best practice on these matters. What you have here are a number of images of products that have failed due to hydrogen embrittlement. I'm going to pick up on a point that Mark mentioned earlier. The challenge with these issues that you see here is that they happen from the inside out. The accumulation of the hydrogen happens within the steel structure. It's not like a surface crack or wear. It happens from the inside out, and it creates the internal pressures that then go and break. So we're aware of failures in different territories around the world. The recent one we've been advising on was in Brazil, where product and chain and slings have broken when not under loan. So it happens from the inside out with no warning, and therefore it's catastrophic. The people around the lifting environment have no notice, and therefore the risks to the individual and to the asset is significant. So the image at the top left is a swivel hoist ring, a very familiar product, a very reliable product, fundamentally though designed for onshore lifting applications. And in this case, clearly what it shows is that the bolt in question here was too hard. Okay, I don't believe there's a problem at all with any of these products with the manufacturing process. It's the fact that their selection for use offshore has been proven to be inappropriate. Okay, we have a number of master links down here that have failed on DNV welded chain slings in different configurations here. It happens from the inside out. So I just wanted to talk about here what makes a steel susceptible. And I think I've touched on it already. The simplest way to understand it is hardness. So the harder the steel, the more susceptible it is to hydrogen embrittlement and therefore to hydrogen-assisted stress cracking as a result of that. Now, the simplest, and there are other factors that contribute to the hardness of a steel, is the carbon. The carbon content is a simple and cheap and effective way of making a steel extremely hard and giving it a high working load limit, which perhaps onshore, when there's no dynamic load amplification or anything going on, is perfectly suitable. But offshore, it comes with risks and is less than ideal. The other factor here is heat treatment. So on this slide, you will see that as the carbon content in a steel increases, it's almost precisely proportional to the hardness. Now, we actually want a product offshore that is tough and ductile, and therefore you have to add different alloying elements such as nickel, aluminium, etc. Okay, so you get the right blend of hardness, i.e. tensile strength, and ductility stroke toughness. The other subject we touched on there was heat treatment, and with Francois and Professor Rolf Mustert, they are absolute experts in this. So for a given grade of steel, if you temper it at 200 degrees for a very low period of time, you end up with a steel that is extremely hard and in effect would give you a good working load limit. However, its toughness is not very good. If there's a snatch on the load, corrosion, it's not great. The manufacturing process that we believe should be going through takes you through a higher temperature and for greater length of time so that the toughness and hardness combined. Now, as a manufacturing process, that obviously takes longer, requires more energy, and therefore makes the product more expensive, but it makes it suitable for the environment that we're talking about and the applications that we're discussing. Now, for every grade of steel, raw material that you're talking about, if you put it through the same process, you'll get a slightly different product attributed to well. So the consistency of the raw material and the manufacturing process must be aligned. So what we've done in a number of these sessions with companies around the world is saying, well, okay, you're faced with these issues. Here's we believe that you should specify and what you should be looking for in products for the offshore marine environment, so that these risks, they are designed to cope with these risks. So what you have on here is a range of products, some of which we've had available for some time, but some are fairly new. And as a result of the research and the findings that we've had from the market, the customers, our industry experts in terms of McKinnon, and also the likes of the research bodies that are represented here. So the Master Link range at the top left, we have had in the marketplace for many years. We've supplied over 500,000 of these products, and they're specifically designed so that they have a maximum hardness, this product, of 36 Rockwell C. So I just want to pick up on that. And along with that product, it's a great product, but it's ductile. It's designed for the environment. We've recently introduced a range of marine grade chain. This is the same chain that goes into the D&V welded chain slings that go into the Norwegian market. Okay, so in Norway, they use the welded chain slings. We've recently gained approval from D&V for type approved mechanically assembled. So we can actually make, rather than welded, we can make mechanically assembled chain slings in the UK and dispatch. But the chain used has a maximum hardness of 38 Rockwell C, and it also comes with a zinc tough finish on that delays the onset of corrosion. It also has non-spark attributes, and its major strength is its toughness and ductility. I don't propose in terms of today to go into a lot of detail on our subsea chain blocks and our lever hoist, other than to say we use grade 8 low chain on there. We have the option of grade 10, but we believe in the same way that grade 10, which is typically associated with a harder chain, is not ideal and runs risks. It is not to say that you can't get a grade 10 with a hardness level that makes it appropriate, but it then becomes difficult. Typically grade 8 is better suited because it's not as hard. Okay, so our hoisting range uses grade 8, which in terms of the low chain for the reasons we've discussed, and in terms of the other products on there, the ROV products and self-locking hooks are all designed for this environment. So that brings to conclusion the background, the research, we can share with you. You can download the technical paper that goes into more detail. We're happy to give, as I say, technical briefings to any William Hackett distributor, to any end user, as we call them. But I'd like to now hand back to Maria, who will open up the Q&A and the questions and the discussion. So I'd really encourage you to pick the brains of the likes of Mark Taylor from an operational perspective, and also the likes of Francois and Ralph regarding industry expertise on both steel and hydrogen embrittlement. Their knowledge goes way beyond mine. Maria, over to you. Thank you.
Thank you, Ben. I think we have to unshare your screen. Lovely. Thank you. Thank you very much, Ben. Very interesting. I think I followed some of that. Very technical stuff. Now, I'm seeing the questions are starting to come in, but just as a starting point, a general question. Perhaps for you, Rolf, how is hydrogen embrittlement impacted when there is a treatment to the surface of a material? I think you were talking about peening earlier in your introduction. Can you talk a little bit about how various surface treatments can affect hydrogen embrittlement?
Yes, so hydrogen embrittlement can be classified as either external hydrogen embrittlement or internal hydrogen embrittlement. The type of hydrogen embrittlement we're talking about here in the offshore industry is mostly externally driven. In other words, the reaction of the environment and the surface of the component of the chain is such that hydrogen is generated during the corrosion process. So any coating that will delay or prevent the hydrogen from being generated during corrosion, in other words, any coating that will be effective against corrosion will essentially remove the cause, will remove the hydrogen that is generated during corrosion. So surface coating, and I see that there's been reference made to zinc surface coatings, are quite effective in protecting the chains from corrosion and from hydrogen embrittlement.
That's very interesting. We have a question from Patrick Blacken, and he says, we are a cleaning company focusing on all things industrial. We've had inquiries about removing paint from lifting equipment, but have had issues as customers are worried about using our chemicals on the equipment. Is there any way to clean or remove paint without causing hydrogen embrittlement? Have you any advice for Patrick?
Yeah, so grit blasting or shot blasting is a non-chemical method, and that is quite effective in removing the coating without incurring any hydrogen damage.
And Mark, how do you clean product at Total, or do you not go down that route ever?
To be honest, we don't clean them, we just get them replaced. If we have any issues, then we'll just replace it, because the risk to us is just too high compared to the costs. Yeah. We're not looking at the cost of the equipment, we're looking at the cost to us if we have an incident.
Sure. And another question.
Can I ask Francois a question, a leading question here, Francois? I think that where the gentleman's going from is perhaps the use of acid in some manufacturing process and acid in the cleaning processes, Francois. Would you like to just comment and perhaps pick up on that one? I know it's something that we've been asked in various customer meetings over the years.
Oh, thank you, Ben. I think as far as an acidic substance is concerned, hydrochloric acid and the likes is one of your main problems that can create hydrogen embrittlement. So when you do employ cleaning, for instance, when you galvanize products using hydrochloric acid, and you have to make sure that you clean properly and you rinse properly. If you can apply coatings without an acidic part of the process, typically our zinc tough process where it's a dry process, there's no acid involved, you still get the zinc tough coating, is actually ideal, and you eliminate that risk. But certainly any acid poses a problem. Also, when you clean stuff cathodically, it can also pose a problem. Plating, when you plate stuff, you generate hydrogen, and you need to take care. Some cases you need to bake your product if you can to get rid of the hydrogen. But yeah, acid cleaning can be an issue.
We have another question here from an anonymous attendee who says, hardness should be measured through the material diameter, not the surface. He would appreciate, or she would appreciate, your opinion. Perhaps Ben?
Francois is the subject matter expert in this area, along with Professor. Yeah.
I think Rolf can also come in here, but from my side, obviously, yes, I agree with that. Hardness should be measured throughout the section thickness. Normally, when you have a hardenable steel, the difference between the surface and the core is very little. But certainly, I do agree one should take into account the whole cross-sectional area. But typically, on your surface, you would have the higher hardness, and towards the center, your slightly lower hardness. I don't know if you agree with that, Professor.
Yes, due to the hardening process during quenching, it's quite true, as Francois indicated, that the surface is likely to be harder than the core. So the surface is typically the worst case location in terms of hydrogen embrittlement. It's also where the hydrogen cracking will initiate. So technically, it is correct to say that one should do hardness checks through thickness, but from a practical point of view, as Francois indicated, the highest hardness is expected on the surface, and that's also where the cracking initiates.
Francois and Professor, I'm going to ask another question here because I know the questions that we've been asking from the customers. Can you explain the importance of hardenability, which was a terminology that you just referred to there, which I'm familiar with, but I think some of the guys on the call may or may not be familiar with because it's an important attribute.
Look, hardenability is the ability of the material to through harden for a certain section thickness. In other words, to achieve the same hardness throughout the diameter or the thickness of the material, typically influenced by alloying elements such as chrome, nickel, molybdenum, where carbon gives you a hardness, which is a hardness value, the material property. These other elements, they also add to some extent to your strength, but they're mostly there to improve the through hardenability. So through hardenability means to have the right hardness across a diameter, where hardness is a measurement that you take in a certain position. Rolf, I don't know if you want to link on to that.
Yes, Francois hit it on the head there. So the response of the steel to the hardening process can either be such that you get full through hardening, or you can get shallow hardening. And the property that governs that is called the hardenability of the steel. So good hardenability will make for good through hardening, and poor hardenability will make for poor through hardening. And it is the alloying elements, as Francois indicated, that retards the transformations, and by retarding the other transformation products which are softer, one then ensures that you get the hard martensite forming during quenching.
Thank you. We've got a few questions on the subject of temperature. I'll start with this one, which is what test temperature do you suggest? -20 or -40 degrees C? Rolf?
Yeah, I think it's an industry norm. I guess Francois might be a bit suited to answer that one.
Thank you, Rolf. Look, -20 is the norm in the offshore industry at the moment. The DNV requirements call for -20. Obviously, the lower your product at the lower temperature can still give you an adequate joule value at impact, the more safe that product is. It all depends on the design temperature. If your design temperature is -20, then you should meet the requirements at -20. If it's -40, you should meet it at -40. By the way, this is also a function of your material property. Your alloying elements, especially nickel, plays a very significant role in low temperature toughness. So I would say, yeah, temperature is important. Make sure that you test at the temperature where your product's being applied, or maybe slightly lower, just to build in a bit of a safety factor.
So following on from that, we have another question which says, at what temperature during the service life should we start to have concerns as to structural change and increased risk of hydrogen embrittlement?
Can I add to that question? And Francois, apologies, mate, it's coming to you again. So each steel and each product has different attributes, and the heat treatment will vary that again. It's also linked to the ductile brittle transition temperature, and that is one of the fundamental things that the industry needs to understand, in my opinion. Francois, do you want to pick up the question and my comment around DBTT?
Yeah, if I understand the question correctly, Maria, the question is not so much high temperatures, but at the lower temperatures, where should we be careful of? Now, Rolf must also come in here, but we know that hydrogen is effective in entering the steel at room temperature. As temperature increase, hydrogen tends to diffuse away from the crack tip. So from room temperatures and lower, I think even down to -20 could still be a problem, and even lower than that. Rolf, I don't know if you want to give your comments on that.
Yeah, so Ben referred to a concept in terms of DBTT, and that is the ductile to brittle transition temperature with steels, and particularly with heat-treated steels. You get this characteristic that as the temperature is decreased, you suddenly get into a temperature region where the steel becomes rapidly brittle with a small change in temperature. And this transition temperature is referred to as the ductile to brittle transition temperature. Now, where that temperature lies depends on the heat treatment. And I think Ben then referred to certain products being heat treated so as to have appropriate ductile to brittle transition temperatures, so as not to cause problems at -40 or so. But generally, it is true to say that at the lower temperatures, the fracture toughness of the material is lower, and that the sensitivity for small cracks running into catastrophic fractures becomes bigger. So generally, as temperature decreases, the risk of a small hydrogen crack causing a catastrophic failure increases.
We have a couple of questions that relate to people working with forklift trucks or testing forklift truck chains in cold environments, in chilled environments. And they'd like some advice as to what they can, or how you should check it and what you should say to your customers in terms of explaining to them about hydrogen embrittlement in those chilled environments. I know this isn't offshore, but it's obviously another area where hydrogen embrittlement can occur.
Maria, did you say what the specific chains is it? Is it fork truck?
Forklift truck chains, the load chains.
Okay. I'm not very familiar with that specific application. Rolf, I don't know if you are familiar with that.
No, unfortunately, I'm not.
I mean, would there be some general advice to people who are using equipment in those chilled, I suppose, refrigerated environments, as to how often, or should
Maria, can I just add, I don't know the specifics of forklift chain. It's typically a different sort of chain that's used for forklifts. It's not typically, it's what's called roller chain. So I'm guessing my advice would be to refer to the manufacturer's guidance on that. I would hope that the manufacturer has approved the product, the forklift, and its operating parts for use in that environment to that temperature. And along with that, that they would provide guidance. So the likes of Mark Taylor in his role offshore, as products come to, the first thing that he will do and analyze is the suitability of the product, what's required, inspection, safety factors, all of these things. And likewise, I'm sure that the forklift truck manufacturers will have provided that. So I'd refer back to the manufacturer's guidance in this matter. And there will be an industry standard that refers to it as well.
Perhaps I could pass the details of those questions over to you later on, and
yes,
help the chaps in a bit more detail.
Certainly.
Okay, we have a question that said, which hardness levels would achieve the best results? I assume that is the best results in preventing hydrogen embrittlement occurring.
So I think this is for Francois, and I think it varies depending upon the product and the manufacturing, but there's some general guidance. So Francois?
Ben, hardness, we found below 38 Rockwell C in general is the norm where you should stay. So, you know, if you go over that, you start to get issues with hydrogen embrittlement. But I think it's also a function of not only harness, I think it's probably a combination of microstructure as well, your precipitates, the cleanliness of your steel, grain size, etc. There's quite a few things, but I think hardness is a big indicator, and we found that as hardness go up, your tendency for hydrogen embrittlement certainly increases quite dramatically as you go over 40 and upwards. We're actually busy with a project with Prof. Mostert at University of Pretoria, where we actually want to determine the threshold value for a certain set of product characteristics for hydrogen, the threshold value. So we're halfway with that project, but that's typically the type of project, if you've got a specific chemistry where you can determine for your product what is the cutoff point, the safe cutoff point for the certain working load limit in terms of hydrogen embrittlement. So, but certainly I think my opinion is try and stay clear of hardnesses above 38 for the offshore environment. I think that will be a safe approach. I don't know if you agree with that, Prof. Mostert.
Yes, certainly. We have also encountered in the construction industry with high strength bolts, high strength fasteners, grade 10 versus grade 8, that the 38, 36 rock or sea level is really where one should try to focus on to prevent hydrogen embrittlement.
Thank you. Mark, I think this might be one for you. So recently there have been discussions regarding the use of pipelines, even decommissioned oil and gas pipelines, for the transmission of green hydrogen from offshore wind farms. Any comments on the advisability of that and the effects on legacy equipment?
Generally, the pipelines that we deal with are very well covered with this. Unfortunately, it's been the lifting industry that's been slow to pick up on this issue. But the materials people that's involved with pipelines and that kind of equipment have known about this for decades, and they have very strict rules and limitations on the pipelines for that particular issue. So it'd be going back to the materials tier of the company to ask them the question, what do they accept? Because I know our tier is very strict on what he will accept for material grades of pipelines for transmission of oil and gas products.
Does anyone else have any comments on that? No, okay. This is an interesting one, I think. And this is as a rigging inspector doing visual inspections on chain slings, are there any signs that I can spot indicating that there may be HE occurring on the links and parts of the chain sling? I think that's something everybody'd like to know.
I'm sure it is, but I think Mark is probably the best place in this one, because it's part of his daily routine and schedule of his team. It's a huge challenge, and it's not a simple one.
We've looked at, through the investigations that we've carried out on field lifting equipment with some of the UK's labs as to what methods we can use for detecting this. And the answer comes back, well, yes, if you send it into the lab, we can detect it for you. But on site, no chance. Because you're talking about grain boundaries and the method of the hydrogen getting into the materials and all that associated with it, there's no real way of spotting this when you're doing your normal SI 2307 inspections offshore. And there's no technique that can be used remotely to actually inspect this equipment to identify that there's a potential failure there.
Yeah,
the answer is no.
Yeah, Maria, can I just add to what Mark has said there? Mark's absolutely spot on. So unless as an industry, which is why we're doing this, we start to get a better specification of materials that are suitable for use offshore that mitigate against these, that we will be faced with these failures going on. Because as Mark has said, you can't take a length of chain offshore and inspect and take a micro lab structure, whatever, to every single link. It's not possible. So what people tend to do is they'll just make a superficial judgment based upon it, either its wear or its degree of corrosion and or how long it's been in the field. And they might know it's got to be bin. As Mark said, it's not worth the risk. So this is why if a product is designed and, as Professor said, coded and treated correctly, the corrosion will not be as aggressive, it'll be slowed down, and the material will be known, and there'll be confidence that it is designed to deal with hydrogen embrittlement and the ingress of the hydrogen within the product whilst maintaining its working load limit. So there's no shortcut to this one, sadly.
Okay, thank you. I think that's actually the crux of the matter, isn't it? That you can't see it. This is interesting as well. There were issues with HE in the 80s when the industry moved to 8 and hardness at the grade 8 level was identified as a problem. This was overcome by manufacturers delivering product with the optimum balance of hardness and ductility. Is it fair to say that the best way forward on grade 10 is for manufacturers to come to the same conclusion of balance on hardness and ductility? Francois, what do you think of that?
Maria, thank you. Look, balance of hardness and ductility is obviously a material property that you need to look at. In our opinion, when you have a grade 10, the hardness is just simply, for the lifting equipment, is just simply too high to mitigate that risk. Obviously, you have to meet your design requirements. You know, even for grade 8, you have to have the right manufacturing processes to still be able to mitigate the risk of hydrogen embrittlement. So it's not only grade 10. Even if you manufacture grade 8, your processing parameters and what you do to your product, there's certain things you need to do and treatments to mitigate this risk. So even grade 8 needs special care in this environment.
Thank you.
Can I just add to that? I referenced in my introduction presentation work that we've been doing in Brazil for a major offshore contractor. That was a failure of grade 8 chain under no load. So I want to be quite clear that whilst grade 8 and grade 10 are important factors, the material attributes are actually the fundamental, the foundation of this issue, as Francois has said. So it's not just as simple as grade 8 or grade 10. It is about understanding the material and its mechanical attributes. So this was a grade 8 product that failed. It had a hardness north of 40 Rockwell C42. Now, typically, you're then heading into a grade 10 product range in terms of hardness. So we have to be careful between grade 8 and grade 10, but it's the attributes of the product, mechanical attributes that we have to focus on here, Maria.
Yes. Thank you. There's a question here specifically for Mark, which says, I'll find it again. Let me have a quick look. Or before I get to that, there are certain organic coatings on grade 10.9 fasteners claimed to avoid HE as compared to hot dip galvanized fasteners. You mentioned coatings help protect against HE. How does hot dip galvanizing cause HE? Perhaps Professor Rolfe, that's one for you.
Hot dip galvanizing as a precursor surface treatment and surface cleaning processes, and often those cleaning processes make use of acid pickling. So the acid pickling that precedes hot dip galvanizing is often the culprit in terms of providing a source of hydrogen. What you also get with galvanized coatings, hot dip galvanized coatings, specifically in terms of fasteners, is that the application of the fastener load causes cracks in the hot dip galvanizing. And those cracks typically occur at the roots of the threaded portions of the fasteners. And you then get a localized cathodic cell that is often a source of environmentally assisted hydrogen embrittlement at the cracks in the hot dip galvanizing coating.
Thank you. Does anyone else have anything to add to the subject of galvanization? Okay, thank you. I think we'll probably make this our last question. And the question is, if we have a lifting product that is subject to heat, at what level should we start to be concerned? I assume just concerned about hydrogen embrittlement.
Maria, you're talking about high temperatures, I suppose?
Yes, I think so, yes.
Okay, so the general rule is normally for grade 8 chain, you shouldn't get any softening effect up to 400 degrees, although if you work in the range of, let's say, 200 to 300, there will be a reduction in working load limit, which the manufacturer normally specifies in his data sheets. If you exceed that temperature, you will cause a softening effect in the steel, a tempering back, and obviously the strength will go down. As far as hydrogen is concerned, I don't think hydrogen is a big issue. Rolf, you must just add here, at the higher temperatures, as I said earlier, the hydrogen tends to diffuse away from the crack tip at higher temperatures, making it not so detrimental. Do you agree with that?
Yes, that's spot on, Francois.
Thank you. Gentlemen, I think we've answered all the questions that our attendees have asked. I mean, if anybody does have any questions once the webinar is over, please send them to me and I can redirect them to our panelists at a later date. Perhaps each of our panelists would like to just give a short statement of what you'd like people to really take away today. What would be one most important thing for them to realize about hydrogen embrittlement? Perhaps Rolf, you would like to go first?
Yes, I think the risk associated with hydrogen embrittlement fractures have I think, featured strongly in the discussion. And the fact that hydrogen embrittlement and hydrogen embrittlement fractures are insidious and often difficult to detect in time is also, I think, a very important point. And therefore, as Ben's slideshow showed, the best way to address this issue is to look at the susceptibility side of the equation and ensure that the susceptibility to hydrogen embrittlement is in fact good, superior.
Thank you. Mark, what would you like people to take away with them today?
Acceptance. Big word. Basically, historically, the lifting industry has not accepted this as being a big issue. Time and time again, when I'm talking to people about hydrogen embrittlement and stress corrosion cracking and da-da-da, it comes back, well, I've never seen that, therefore it's not an issue. Historically, the problem is that when we've had failures, it's easy to put it down to overload, when it's not always overload. Sometimes it's because of hydrogen. So it's acceptance that there is a problem here and that we should be dealing with it, not as 3 or 4 individuals, but as everybody. The whole industry needs to look at it.
Thank you. Francoise, what are your thoughts?
Maria, in closing, I would like to see our national and international standards addressing this issue. They're good standards, but they're not specific about the hydrogen embrittlement threat. And even with grade 8 chain, you only got minimum specifications. There's nothing about maximum hardness. So I think going forward, our bodies that govern these things and these specifications must come to the table. We have to put something in there to protect the industry and to mitigate this risk also at that level.
Thank you. And Ben, final word?
So I'm going to probably make three requests, if I can here. Building on what Francois said, we're very keen that the classification organisations such as API, DNV, Lloyd's, etc., start to address this and document it, and so that it then provides the guidance to the industry. I think Mark is correct that a number of manufacturers have been very cautious about saying, yes, we recognise it, because they don't want to be associated in any way with a failure. So my offer here is both to my rigging shop customers, the end users, and to the competitors who are on this call with us, is to say, come on, guys, let's work together to make this a safer industry. If we do so, we're going to raise the bar, and the credible manufacturers and supply chain partners will survive and it will create a safer environment. So I'd just like to say thank you to the guys who've taken the time, the panelists, Mark, Rolf, Francois, etc., and Maria to Lift and Hoist for organising this. Thank you.
Thank you, Ben. And if I can also add my thanks. Thanks to our attendees, and thank you for being so engaged with the presentations. And thank you very much to our panelists. I'm quite excited because there's actually a question I can answer, which is, will you be able to watch the webinar later? Yes, we will be creating a video for you and sending it out as soon as possible. So thank you very much, everyone, for coming today. Thank you to our panelists, and have a very good afternoon.